diesel cycle, the ideal cycle for the compression ignition engines. As we discussed last time, in the operation of diesel cycle, there are some main differences with the Otto cycle. The main difference is in an Otto cycle or spark ignition engine, there is a spark plug. Air-fuel mixture is compressed during the compression stroke, and spark plug ignites the fuel close to the top dead center, and the combustion takes place as a constant volume process, almost. In diesel cycle, only air is compressed during the compression stroke, and because of the high compression ratio compared to the Otto cycle, air is compressed to very high temperatures, higher than the self-ignition temperature of the fuel. As a result, when the piston reaches close to the top dead center, fuel is injected by a fuel injector instead of a spark plug at the top of the cylinder. In diesel cycle, there is a fuel injector, and at the end of the compression stroke, where the air is compressed to a very high temperature, which is above the self-ignition temperature of the fuel is injected in small, fine droplets, and once there is a contact with the hot air, the temperature of the fuel suddenly increases above the self-ignition temperature, and the self-ignition starts. Okay, so the self-ignition starts when the fuel is injected into the hot air at the end of the compression stroke. And for this to happen, compression ratio should be high, and usually it is between 12 and 24. Okay. Okay. So here you see PV, pressure, specific volume, and temperature entropy diagrams of the ideal diesel cycle. Process 1, 2 on the left diagram. So let's look at the left diagram. Okay. Okay, on the left diagram, on the PV diagram, as you can see, so let me take this on the right-hand side. Okay, so the process 1, 2 is isentropic compression process, where air is compressed in a piston cylinder device from 1 to 2, and the piston travels from bottom dead center to the top dead center. This is the level. And at 2, between 2 and 3, you have heat addition process, which is replacing the actual combustion process in the cycle. And the combustion process is modeled by a constant pressure heat addition process, the process 2, 3. In the real engine, between 2 and 3, you have the combustion process, but the combustion starts close to the top dead center and continues well into the expansion stroke, so that as the fuel injection continues, combustion continues, and you have almost constant pressure operation. As a result, this process is modeled by a constant pressure heat addition process between 2 and 3, Q in. And 3, 4 is the isentropic expansion process. As you can see, 3 starts after top dead center, and it continues until 4, which is the level of bottom dead center. And this is the isentropic expansion process. The other name for this process is power process. Okay, between 4 and 1, you have constant volume heat rejection process. This is the same as Otto cycle. And in reality, in the actual cycle, this process is replacing the exhaust blow down process, which actually happens slightly before bottom dead center when the exhaust valve opens. Most of the exhaust gases go out of the cylinder, and then this process is modeled by this constant volume heat rejection process. Process 4-1. Process 4-1. Okay. Process 4-1. On TS diagram, as you can imagine, process 1-2 is constant volume heat addition process, and process 3 constant entropy. Process 1-2 is isentropic compression process, because entropy is constant, and the process 3-4 is isentropic expansion process, during which entropy is constant. So isentropic process means the process is reversible and adiabatic. And process 2, 3, and 4, 1 on constant volume processes, heat input and heat output respectively. Okay. Okay, this is the Otto cycle on the PV and TS diagrams. So this is the diesel cycle. What is the difference between Otto cycle and diesel cycles in this diagram? Or look at the PV diagram. What is the difference between Otto cycle and the diesel cycle in terms of the PV diagram? Anybody with the answer? I asked a question. The question is, what is the difference between Otto cycle and diesel cycle in terms of this PV diagram, pressure, volume diagram? Okay, I have one answer, which is not really what I am looking for, but thank you for the answer anyway. Any other answers for this question? So do you remember how Otto cycle looks like? Okay, let me try for you in this diagram. Okay, let's have this. This is pressure. This is specific volume. And this is the compression process. Okay. This is the heat addition process. This is and this is 1. This is 2. This is 3. This is 4. So this is isentropic compression process 1, 2. This is 2, 3 constant volume heat addition process. So you have Q in here. 3, 4 is isentropic expansion process. And the 4, 1 is constant volume heat rejection process. Q out. So this is Otto cycle. Otto. So you can easily see the difference between this is your diesel cycle, ideal diesel cycle. This is your ideal Otto cycle. Clearly, you can see the difference. Which process is different? What is the main difference? Yes, Onur and Yusuf answered these questions correctly. So the difference is the heat addition process, right? In diesel cycle, heat addition process is modeled by a constant pressure heat addition process. And in Otto cycle, it is modeled by a constant volume heat addition process, process 2 and 3, process 2 to 3. Okay. Okay. I can erase this now because if I don't erase it, then it stays like this. Let me erase it for you, for myself. Okay. Idea is given here. Let me have my pointer. Okay. So here we have equations. We have the equations, thermodynamic equations, thermodynamic analysis of the ideal diesel cycle. The ideal diesel cycle. First, okay. So the general relation is if you have heat input and the boundary work output for a closed system, heat input minus boundary work output is equal to internal energy difference. And you can write that between 2 and 3. This is the constant volume heat addition process. And if you write it, you will see that it is equal to, here you can solve for Q in, and the Q in will be internal energy difference plus the boundary work output. For process 4.1, heat rejection process, heat output is equal to U4 minus U1. If you use constant specific heat assumption, delta U can be represented by CV delta T, which is given here. Of course, there is no boundary work here, so we don't have this term here. And for process 1 and 2, 3 and 4, these are the isentropic processes. So we can use the work relations for isentropic work from chapter 4, at the beginning of chapter 4, when we discuss boundary work. They are, if you write the energy balance relation between 1 and 2 and 3 and 4, you will see that work input during the isentropic work process is equal to U2 minus U1, okay, internal energy difference, and which is approximated by using constant specific heat assumption CV T2 minus T1. Similarly, work output during process 3-4 is equal to work out is equal to U3 minus U4, and that is equal to CV T3 minus T4. Okay, so for each process also you can apply the ideal gas relation, as we will see in the solutions of some problems. So using Q in and Q out, you can express thermal efficiency of the diesel cycle as net work divided by heat input. Net work is Q in minus Q out. As a result, thermal efficiency of the diesel cycle is 1 minus Q out over Q in. And Q out given by this formula, Q in given by this formula. Here, I didn't discuss with you, but delta U plus boundary work during a constant pressure process is equal to delta H, and we utilize that for Q in. Q in is, as a result, enthalpy difference between 3 and 2, which is approximately equal to Cp delta T, using constant specific heat assumption. Okay? Again, we are able to do that because pressure is constant during the heat addition process. So substituting Q out and Q in results here in the thermal efficiency formula and doing some manipulations. And we have to make a definition for cutoff ratio, RC, V3 over V2. So the volume ratio, or the specific volume ratio between 3 and 2, is called cutoff ratio. And using this equation, we end up with this relation for the thermal efficiency of diesel cycles. So when you look at this result, you will see that first of all, this result is obtained under the constant specific heat treatment, right? Because all these formulations are based on constant specific heat analysis. As a result, this result is based on the use of constant specific heats for the air properties. And once we have this relation, we can examine it, and we will see that thermal efficiency of ideal diesel cycle is a function of 3 parameters. One is R. What is R? Okay, R is the compression ratio. RC is, we just defined as cutoff ratio. And what is K? Do you remember what K is? Probably you are writing the answer as I speak, and I can see that somebody wrote it already as Cp over Cv, which is correct. What is the name of that? The name is specific heat ratio. Okay, so the thermal efficiency of the diesel cycle is a function of 3 parameters: compression ratio, cutoff ratio, and specific heat ratio. And if you analyze this equation for the same compression ratio, you will see that thermal efficiency of the Otto cycle is greater than thermal efficiency of the diesel cycle. Because here, what is the thermal efficiency of the ideal Otto cycle? Do you remember the equation? Equation is this part, right? This one. So let me show it like this. So this is your thermal efficiency of the Otto cycle. This is the one. Okay. So what is the effect of the term in the bracket? Because RC is always greater than 1, because V3 is always greater than V2, K is always greater than 1, okay? As a result, if you mathematically analyze the term in the bracket, you will see that this term is the effect of this term is to decrease the thermal efficiency based on this part, which is the Otto cycle efficiency. So this term is less than 1, and which will decrease the efficiency. As a result, we can say that for the same compression ratio, Otto cycle thermal efficiency is greater than diesel cycle thermal efficiency. Okay. Okay, here, thermal efficiency of the diesel cycle as a function of compression ratio is given. Again, when you look at this equation, the idea of the effect of compression ratio on the diesel cycle efficiency is clear. The higher the compression ratio are, the higher the efficiency of the diesel cycle. If you mathematically analyze the effect of RC, which is the cutoff ratio, the higher the cutoff ratio, the lower the efficiency of the diesel cycle. When RC is equal to 1, what happens? When cutoff ratio is equal to 1. What does that mean? Okay, any answer to my question? No question yet. No answer yet. Okay, so if you analyze this equation mathematically, you can easily see that when RC increases, thermal efficiency decreases. And under what conditions RC is equal to 1? When V3 is equal to V2, which is the case? When is this the case? When is this the case? It is the case in the Otto cycle, right? So when RC is equal to 1, this equation reduces to the equation for the Otto cycle. That means in that case, efficiency becomes much higher. So the higher the RC, the lower the thermal efficiency of the diesel cycle. And the effect of K is to increase the efficiency of the diesel cycle. Okay. So let's look at this diagram closely. If we look at this diagram closely, we will see that as the compression ratio increases, thermal efficiency of the diesel cycle also increases. Okay. And you can also see the effect of, so as the compression ratio increases, thermal efficiency increases rapidly in the low values of compression ratio. Then the increase becomes relatively small at higher compression ratios. And this colored area shows the effect, the typical compression ratios for diesel engines. And here RC is equal to 4, 3 to the cutoff ratio. As you can see, when the cutoff ratio decreases, the efficiency of the diesel cycle increases. In the limiting case of RC is equal to 1, the cycle reduces to Otto cycle. Okay. Okay, any questions? Are there any questions? Okay, there are no questions, so let me continue with the next cycle, which is the dual cycle. So the dual cycle, so diesel cycle is the ideal cycle to represent actual diesel engines, compression ignition engines. But in modern diesel engines for fast, modern high-speed compression ignition engines, actually the fuel ignition times, fuel injection times at the end of the compression stroke is a little bit early. So in modern diesel engines, the fuel is injected earlier during the compression stroke, towards the end of the compression stroke. As a result, there is a period of combustion for which combustion is almost at constant volume. And as fuel injection continues towards the expansion stroke, then part of the combustion during that part is almost at constant pressure. As a result, the combustion process can be modeled by two processes, 1, 2 to X, constant volume heat addition, X to 3, constant pressure heat addition. So this cycle is called dual cycle, and this is a more realistic model, realistic ideal cycle model for modern high-speed diesel engines. So this is the only difference. The model of combustion process is the only difference between diesel cycle and dual cycles. So both diesel cycles and dual cycles are the ideal cycles representing compression ignition engines, but diesel cycle is a better representation for old diesel engines, but the dual cycle is a better representation for the modern diesel engines. Okay. So how do we analyze this cycle mathematically? So it is easy. So from 2 to X, Q in. So let me show it for you. So Q in during process 2X is equal to, what is the formula? So it's the constant volume heat addition. There is no boundary work. So it is equal to UX minus U2, right? Very easy. So let's look at process X3, which is the constant pressure heat addition. So there is heat input Q in during process X3, which is equal to, this is heat input. And during, this is an expansion process also towards the expansion stroke between X and 3, minus boundary work output is equal to energy change of the closed system, which is the internal energy change, which is equal to U3 minus UX, right? So this is the formula, energy balance formula for process X3. If you solve for Q in X3, which is equal to du plus boundary work, which is equal to dH, which is equal to H3 minus Hx, right? Okay, let's continue. Okay, how can we express that? Using constant, if you use constant specific heats, this is equal to Cp E3 minus Tx. Okay, so we have the equations for heat input during process 2X, which is Ux minus U2, which can be expressed by using constant specific heats. Cv Tx minus T2. Okay. Okay, let me ask you the same question I asked you before. Why it is Cv here when we express Ux minus U2? We have Cv delta T. When we express H3 minus Hx, we have Cp delta T. Why is it Cv here? Why is it Cp here? So tell me here, first question, why is it Cv here? Why is it Cv here, not Cp? Okay. Okay, constant volume is the wrong answer. Correct answer is because it is the internal energy change, right? If it is internal energy change, we have Cv here. Why is it Cp here? Because it is enthalpy change we are talking about. The wrong answer here is because it is constant pressure. The wrong answer here is because it is constant volume. These are the wrong answers. The correct answers are, it is Cv here because we are talking about internal energy change. It is Cp here because we are talking about enthalpy change. Okay.